Welcome to the deep dive. Today, we're diving into the world of machine learning. We'll be using excerpts from two books, Hands-on Machine Learning with Scikit-Learn and TensorFlow, and
Yeah.
Hands-on Data Science and Python Machine Learning. So we'll break down the basics, explore some real-world examples, and really see how machine learning is already impacting your life.
It's a fascinating field, and it's evolving so rapidly. It has applications you might find surprising.
Yeah, I'm already curious. So what exactly is machine learning? I mean, I hear it everywhere, but
Right.
is it really as futuristic as it sounds?
Well, it's definitely not science fiction anymore. Machine learning is essentially about letting computers solve problems and find patterns in data without needing a programmer to explicitly code every step. Think of it like this. You want to predict which customers are likely to buy a certain product. Instead of writing complex rules, you feed a machine learning algorithm customer data, their past purchases, browsing history, demographics, and so on. The algorithm then identifies patterns that indicate buying behavior, allowing you to target the right customers.
That's fascinating. So it's not about programming a computer with specific instructions. It's more about letting it figure out its own rules based on the data.
Exactly. And there are different ways machines can learn depending on the type of problem and data. We can broadly categorize them as supervised, unsupervised, and reinforcement learning.
Okay, let's break those down. What's the difference?
Imagine you're teaching a child to recognize different fruits. In supervised learning, you'd show them pictures of apples, oranges, and bananas, each labeled with its name. That's essentially what we do with supervised learning algorithms. We provide them with labeled data, where each example has both the input features and the desired output. The algorithm learns to map the input to the output, enabling it to predict the output for new, unseen inputs.
So if I wanted to predict housing prices, I'd feed the algorithm data on houses, including features like size, location, number of bedrooms, along with their actual selling prices. The algorithm would learn from this labeled data and then be able to predict the price of a new house based on its features.
Precisely. Now, in unsupervised learning, we take away the labels. Imagine giving the child a basket of different fruits without telling them what they are. The child might start sorting the fruits based on similarity, shape, color, size, even though they don't know the names. Similarly, unsupervised learning algorithms are fed unlabeled data, and their task is to find hidden patterns or structures within that data.
So instead of predicting a specific output, it's more about discovering underlying relationships or groupings within the data itself.
Exactly. This is useful for things like customer segmentation, where we group customers based on their purchasing behavior, without knowing beforehand what those groups might be.
That makes sense. And what about reinforcement learning? It sounds a bit more adventurous.
Reinforcement learning is all about learning through trial and error. Imagine teaching a dog a new trick. You reward it for good behavior and correct it for bad behavior. Over time, the dog learns to perform the trick to maximize rewards. In reinforcement learning, an algorithm interacts with an environment, taking actions and receiving feedback in the form of rewards or penalties. Its goal is to learn a strategy that maximizes rewards over time.
So it's like a video game character learning to navigate a maze, getting points for correct moves and losing points for wrong ones.
Yes. A classic example is training an AI to play a game like Pac-Man. The AI learns to navigate the maze, eat dots, and avoid ghosts to achieve the highest score.
Now, you mentioned predicting housing prices earlier with supervised learning. Can we dive a bit deeper into the steps involved?
Absolutely. One key concept is the division of data into training and test sets. Think of it like studying for an exam. You learn from your textbook and notes that's your training data. Then you test your knowledge on practice questions. That's your test data.
So we train the algorithm on one portion of the data and then test its performance on another portion to see how well it generalizes to new data.
Exactly. This helps us evaluate how well the algorithm has learned the underlying patterns and whether it can accurately predict outcomes for data it hasn't seen before.
That makes sense. But I've also heard about algorithms making mistakes, like overfitting the data. What exactly does that mean?
It's a common challenge. Overfitting is like a student memorizing answers for a test. Instead of truly understanding the concepts, they might ace the practice test, but they'll struggle with new questions that require applying those concepts.
So an overfit model performs well on the training data, but poorly on the test data, because it hasn't really learned the underlying patterns, just memorized the specific example.
Exactly. On the other hand, underfitting is like not studying enough. The model is too simplistic to capture the complexity of the data and performs poorly on both the training and test sets.
So it's about finding the right balance. A model that's complex enough to capture the patterns, but not so complex that it just memorizes the training data.
Exactly. That's where techniques like cross-validation come in. Imagine you're studying for an exam with a group of friends, and you each take turns testing each other on different sections of the material. Cross-validation is similar. We divide the data into multiple subsets and train the model on different combinations of these subsets, testing its performance on the remaining subset each time. This gives us a more robust evaluation of the model's ability to generalize.
That's a clever way to make sure the model is truly learning and not just getting lucky with a particular set of training data. So we've talked about types of learning and some key concepts. What about the actual tools of the trade? What are some of the algorithms that make all this machine learning magic happen?
That's where it gets really interesting. There are countless algorithms, each with its strengths and weaknesses, suited for different tasks. Let's look at a few of the most common ones.
Sounds good. I'm ready to get into the nitty-gritty.
One of the simplest and most widely used is linear regression. Imagine plotting data points on a graph and trying to draw a straight line that best fits the trend of the data. That's essentially what linear regression does. It's used to predict a continuous target variable, like housing prices or stock prices, based on a linear relationship with input features.
So if we plot the price of a house against its size, linear regression would try to find the line that best represents the relationship between those two variables, allowing us to predict the price of a new house based on its size.
Exactly. Now, what if we want to classify data into categories rather than predict a continuous value? Let's say we want to determine whether an email is spam or not. That's where logistic regression comes in. It's similar to linear regression. But instead of predicting a number, it predicts the probability of an instance belonging to a certain category.
So instead of straight line, it's drawing a boundary that separates the data into different categories.
You got it. Then we have decision trees, which use a tree-like structure to make decisions based on a series of questions about the input features. Imagine a game of 20 questions, where each question helps narrow down the possibilities until you arrive at the answer.
I love that analogy. So for spam detection, a decision tree might ask questions like, does the email contain certain keywords? Is the sender's address known? And so on, branching out based on the answers until it reaches a decision spam or not spam.
Precisely. Decision trees are relatively easy to visualize and interpret, making them a popular choice for many applications.
This is all making a lot more sense now. What other algorithms are commonly used in machine learning?
Another powerful algorithm is k-nearest neighbors, or KNN for short. Imagine you have a new data point, and you want to classify it. KNN looks at the k-nearest data points that are already classified, and assigns the new data point to the category that's most common among its neighbors.
So it's like asking your neighbors for their opinions and going with the majority vote.
Exactly. It's a simple yet effective algorithm, often used for tasks like image recognition and recommendation systems.
Fascinating. And are there any algorithms that are a bit more complex, perhaps tackling more challenging classification tasks?
Absolutely. Support vector machines, or SVMs, are a powerful class of algorithms that aim to find the optimal boundary, or hyperplane that separates data points into different classes. It's like drawing a line that maximizes the margin between the different groups of data.
So it's not just about finding any boundary,
Yeah.
but about finding the one that creates the clearest separation between the categories.
Exactly. SVMs can handle complex nonlinear relationships between data points, using a technique called kernel functions, which essentially transform the data into a higher dimensional space where it becomes easier to separate.
This is all really intriguing, but I have to ask, real-world data is rarely perfect, right? What happens when there are missing values or outliers that could skew the results?
That's a great question. Real-world data is often messy and requires careful preparation before we can feed it to machine learning algorithms.
So it's like a machine learning spring cleaning. We need to tidy up the data before we can really put it to work.
Exactly. We call this process data preprocessing, or feature engineering. It involves handling missing values, transforming features into a format that algorithms can understand, and even creating new features from existing ones to improve the model's performance.
Feature engineering sounds intriguing. It's like we're not just using the data as it is, but actually crafting it to be more useful for the algorithms.
Got it. For example, let's say we have a data set with a date of birth column. A machine learning algorithm can't directly understand dates. We might transform that into age, which is a numerical feature that algorithms can easily process. Or we could even create a new feature, like days since last purchase, by combining the purchase date with the current date. These engineered features can provide valuable insights that the raw data alone might not reveal.
That makes a lot of sense. It's like taking raw ingredients and turning them into a delicious meal through careful preparation and a touch of culinary creativity.
A perfect analogy. Now, when it comes to handling missing values, we have several options. Sometimes we can impute them, which is like filling in the blanks based on the existing data. For example, if we're missing the age of a customer, we might infer it from their purchase history or other demographic information.
So it's like solving a puzzle where you use the surrounding pieces to figure out what the missing piece should look like.
Exactly. But if the missing values are too extensive or difficult to impute accurately, we might choose to simply remove those data points from our dataset.
It's like deciding whether to repair a damaged garment or simply get a new one if the damage is too severe.
Precisely. Outliers, on the other hand, are data points that are significantly different from the rest of the data. Imagine you're analyzing the heights of people, and you have one data point that's 10 feet tall. That's clearly an outlier that could skew your analysis.
So outliers are like the oddballs in a group. That might distort the overall picture if we're not careful.
Exactly. We can identify and remove outliers using various statistical methods to ensure that they don't unduly influence our model's training.
This data pre-processing step seems crucial for building reliable machine learning models. It's not just about the algorithms, it's also about carefully preparing the data to make sure the algorithms have something meaningful to work with.
Absolutely. Garbage in, garbage out, as they say. The quality of your data directly impacts the quality of your results.
Now, earlier you touched on some advanced machine learning techniques, like dimensionality reduction and ensemble methods. Can we unpack those a bit more?
Of course, dimensionality reduction is like simplifying a complex problem by focusing on the most important aspects. Imagine you're trying to describe an object using 1,000 different features. It's overwhelming, right?
Yeah, it's like trying to juggle too many balls at once.
Exactly. Dimensionality reduction techniques help us reduce the number of features while retaining as much of the important information as possible.
So it's like finding the most essential ingredients in a recipe without sacrificing the flavor of the dish.
Precisely. One popular technique is called Principal Component Analysis, or PCA. It's like finding the most informative directions in the data, allowing us to project it onto a lower dimensional space, while preserving its most important characteristics.
It's like creating a concise summary of a long book, capturing the key plot points and characters without needing to read every single page.
Exactly. Now, ensemble methods are all about combining multiple machine learning models to improve prediction accuracy. It's like having a team of experts with diverse perspectives, working together to solve a problem.
So instead of relying on a single expert's opinion, we're getting a consensus from a group of experts, which is likely to be more reliable.
Precisely. Two common ensemble methods are random forests and boosting algorithms. Random forests create a forest of decision trees, each trained on a different random subset of the data, and then combine their predictions. Boosting algorithms, on the other hand, train models sequentially, with each model focusing on correcting the errors made by the previous models.
It's like having a panel of judges score a performance, with each judge bringing their own perspective and expertise.
Exactly. Ensemble methods are particularly effective when dealing with complex data sets, and can significantly improve the accuracy and robustness of our models.
This whole conversation has been incredibly enlightening. But I must admit, when we started talking about machine learning, I pictured lines of code, complex algorithms, and a level of technical expertise that felt a bit daunting.
I understand. Machine learning can seem intimidating at first, but it's important to remember that it's built on a foundation of statistical concepts and mathematical principles that, while complex, can be grasped with a bit of effort and a willingness to learn.
That's reassuring to hear. So you're saying that even someone who isn't a math whiz can still wrap their head around the basics of machine learning.
Absolutely. Think of it this way. We all use statistical concepts in our daily lives without even realizing it. When you check the weather forecast, you're relying on statistical models that predict future weather patterns based on historical data. When you decide whether to invest in a particular stock, you're making a judgment based on statistical trends and predictions.
You're right. Statistics is all around us, even if we don't always see the equations behind it.
Precisely. And machine learning builds on these statistical foundations. It's about finding patterns in data, making predictions based on those patterns, and refining those predictions as more data becomes available. The algorithms themselves are mathematical tools that automate these processes. But understanding the underlying concepts doesn't require you to be a math prodigy.
That makes a lot of sense. So it's not just about the math, it's about using math as a tool to unlock insights from data and solve problems in a more efficient and intelligent way.
Exactly. And the beauty of machine learning is that it's constantly evolving, making it even more accessible to a wider audience. There are amazing resources available online,
Yeah.
from interactive tutorials and online courses to open source libraries that make it easier than ever to experiment with machine learning and apply it to real-world problems.
It's inspiring to think that anyone with curiosity and a desire to learn can explore this world of machine learning and contribute to its advancement.
Indeed. And as the field continues to evolve, it's crucial that we foster a culture of inclusivity and diversity within the machine learning community, ensuring that these powerful technologies are developed and used in a way that benefits all of humanity.
Speaking of building and using machine learning models, I'm curious about the practical aspects. It's one thing to understand the concepts, but how do we actually put these ideas into practice? What are the tools and technologies that machine learning practitioners use to create and deploy these intelligent systems?
That's a great question. There's a whole ecosystem of tools and technologies that empower machine learning practitioners to bring these concepts to life. One of the most popular programming languages for machine learning is Python. It's incredibly versatile, with a wealth of libraries specifically designed for machine learning tasks.
Python, I've heard of that. It's like the Swiss Army knife of programming languages, right?
Exactly. For data manipulation and analysis, we have libraries like Pandas, which provides powerful data structures like data frames that make it easy to work with structured data. For numerical computations, we have NumPy, which offers efficient arrays and mathematical functions that are essential for machine learning algorithms. And for visualization, we have libraries like Matplotlib and Seaborn, which allow us to create insightful plots and charts that help us understand our data and communicate our findings.
It sounds like a well-stocked workshop for building machine learning models. What about the actual machine learning libraries? Where do the algorithms live?
That's where libraries like Scikit-Learn and TensorFlow come into play. Scikit-Learn provides a wide range of classic machine learning algorithms, from linear regression and logistic regression to decision trees and support vector machines, all implemented in a consistent and easy-to-use API.
It's like a one-stop shop for all your basic machine learning needs.
Exactly. TensorFlow, on the other hand, is a more powerful and flexible library developed by Google. It's particularly well suited for building and training deep learning models, which are computationally intensive and require specialized hardware like GPUs to run efficiently. TensorFlow also provides tools for deploying machine learning models in production environments, whether it's on a web server, a mobile device, or even embedded systems.
It sounds like TensorFlow is the heavy-duty machinery for tackling the most challenging machine learning tasks.
Indeed. And these are just a few examples. The machine learning landscape is constantly evolving, with new tools and technologies emerging all the time. Cloud platforms like Amazon Web Services, AWS, Google Cloud Platform, GCP, and Microsoft Azure offer a suite of machine learning services, from pre-trained models and automated model building to scalable infrastructure for training and deploying models in the cloud.
It's amazing how accessible machine learning has become, with tools and resources available for everyone, from beginners to seasoned experts.
It truly is a democratizing force. Now, I know we've covered a lot of ground here, but before we wrap up, I wanted to shift gears slightly and talk about the real-world impact of machine learning. I mean, it's fascinating to delve into the technical details, but what does all this actually mean for our lives?
That's a great point. We've talked about algorithms, data, and tools, but how is machine learning actually being used to solve problems and improve our lives?
Well, it's already having a profound impact on various industries and aspects of our lives. One area where it's making a big difference is personalized recommendations. Think about the last time you shopped online or streamed a movie. Those recommendations you see are often powered by machine learning algorithms that analyze your past behavior and preferences to suggest items you're likely to enjoy.
It's like having a personal shopper or entertainment curator at our fingertips.
Exactly. And it goes beyond just entertainment and shopping. Machine learning is being used in healthcare to personalize treatments, in finance to detect fraud, in transportation to optimize traffic flow, and even in agriculture to increase crop yields.
It sounds like machine learning is touching virtually every aspect of our lives, often in ways we might not even realize.
It truly is. And as the field continues to advance, we can expect to see even more innovative and transformative applications emerge.
This has been an incredible journey so far, and I'm feeling pretty energized by all these insights into the world of machine learning. What does this all mean? Where do we go from here?
What's fascinating here is that as machine learning becomes increasingly integrated into our lives, it also raises important questions about its implications for the future.
Yes, like what new possibilities might it unlock? What challenges that we need to address?
Exactly. On one hand, Machine learning has the potential to revolutionize countless industries, solve complex problems, and improve our lives in ways we can only imagine. It could lead to breakthroughs in medicine, accelerate scientific discovery, and even help us address global challenges like climate change.
It's exciting to think about the positive impact it could have on the world.
Indeed. But we also need to be mindful of the potential challenges and ensure that machine learning is developed and used responsibly. For example, as these systems become more complex and autonomous, we need to think about transparency and accountability. How can we ensure that these systems are making decisions that are fair, unbiased, and aligned with human values?
That's a crucial point. As with any powerful technology, we need to be aware of its potential downsides and take steps to mitigate them.
Exactly. And that involves ongoing discussions, ethical considerations, and responsible development practices. It's a collective effort to shape the future of machine learning in a way that benefits all of humanity.
This entire conversation has given me a much deeper appreciation for both the power and the complexity of machine learning. It's a field that's full of promise, but it also requires careful consideration and responsible stewardship.
It's a fascinating journey,
Yeah,
exploring how these algorithms are shaping the world around us.
it really is. And this deep dive has given me a whole new perspective on how much machine learning is already a part of our daily lives. But before we wrap up, I wanted to touch on one more concept from the books that caught my attention: transfer learning.
Yeah.
What exactly is that and what makes it so interesting?
Transfer learning is a powerful technique that leverages knowledge gained from solving one problem to solve a different but related problem. Imagine you've trained a machine learning model to recognize different types of cars. With transfer learning, you could take that same model and, with some adjustments, use it to recognize different types of trucks. The model can apply what it learned about car features, like wheels, headlights, and shapes, to more quickly learn to identify truck features.
So it's like learning to play the guitar and then finding it easier to learn the ukulele, because many of the skills transfer over.
Exactly. It's a way to make machine learning more efficient and adaptable. Instead of starting from scratch every time, we can build on existing knowledge, which is especially useful when dealing with tasks where labeled data is scarce or expensive to obtain.
That makes a lot of sense. It's like having a head start in a race because you've already trained for a similar event.
Precisely. And transfer learning is opening up exciting new possibilities in areas like medical imaging, where we can leverage models trained on large data sets of common diseases to more quickly and accurately diagnose rare diseases.
This deep dive has really highlighted the incredible potential of machine learning. But as we've discussed, it's important to remember that technology is a tool. And like any tool, it can be used in ways that are both beneficial and harmful. What are some of the potential pitfalls or challenges that we need to be aware of as machine learning continues to advance?
One key challenge is ensuring fairness and avoiding bias in machine learning models. These models learn from data, and if the data itself reflects existing biases in society, the models can perpetuate and even amplify those biases.
So if a model is trained on data that contains biased hiring decisions, for example, it might learn to make similarly biased predictions, even if factors like gender or race aren't explicitly included in the data.
Exactly. It's crucial to carefully curate and analyze the data used to train these models, ensuring that it's representative and free from harmful biases.
That makes sense. We need to make sure that the data we're feeding these algorithms is a true reflection of the world we want to create, not just a perpetuation of existing inequalities.
Precisely. Another challenge is the potential for job displacement. As machine learning becomes more sophisticated, it's capable of automating tasks that were previously done by humans. While this can free up human workers to focus on more creative and fulfilling tasks, it also raises concerns about job losses and economic disruption.
It's a double-edged sword, isn't it? On one hand, automation can lead to increased efficiency and productivity. But on the other hand, we need to make sure that the benefits are shared equitably, and that those who are displaced by automation have opportunities to adapt and thrive in a changing job market.
Exactly. It's a complex issue with no easy solutions, but it's one that we need to address proactively through education, retraining programs, and economic policies that support workers in the transition to a more automated future.
This conversation has given me a lot to think about. It seems like the key takeaway is that machine learning is a powerful tool with immense potential for good, but it also comes with responsibilities. We need to approach its development and deployment thoughtfully and ethically to ensure that it benefits society as a whole.
Well said. It's a collective responsibility that involves researchers, developers, policymakers, and society at large.
This deep dive has been incredibly informative and thought-provoking. Thank you so much for sharing your expertise with us.
It's been my pleasure.
And to our listeners, we hope you found this exploration of machine learning as fascinating as we did. Remember, the world of knowledge is vast and ever expanding. Keep exploring, keep learning, and keep those deep dives going.